Today, we're going to put together all of those ideas we've been learning over the past couple of weeks about increasing, decreasing, concavity, local maxes and mins to sketch the graphs of curves. And we've done something similar in smaller pieces so far. But we're just going to jump into this example and put it all together, and then we'll do a few examples in class. So in this case, we're working with the function 2x plus 3 over x plus 2. The first thing I want to know is what's the domain of this function? For this particular function, we just have to worry about where the denominator is 0. The denominator will be 0 at x equals -2. So the domain is all real numbers except for -2. So for the x and y intercepts, the x-intercepts are the places that we cross the x-axis. If we cross the x-axis, that means that y is equal to 0. So we set this whole expression equal to 0. We can multiply both sides by the x plus 2 to get rid of that. So our x-intercepts in this case will just be when 2x plus 3 is 0. So 2x is -3 and x is -3 halves. So x is -3 halves. Eventually, we're going to sketch the graph of this function. And so I'll go ahead and start my graph up here. The x-intercept is at -3 halves. So that's -1.5. So that's going to be a place where we cross the x-axis. Okay. The y-intercepts are a little bit easier to find. Those are places when x is equal to 0 because we're on the y-axis. So we just set all of the x's equal to 0, and that just leaves us with 3 halves in this case. So y equals +3 halves. So that's +1.5 is our y-intercept. Okay, so we've got 2 points plotted on our graph here. Let's ask ourselves about horizontal and vertical asymptotes. So we remember vertical asymptotes are places where the denominator is 0 and the numerator is not. In this case, the denominator is 0 at x equals -2. If you plug that into the numerator, you see that the numerator is not 0. So this is our vertical asymptote. So we can go ahead and distinguish that on our graph. And then for horizontal asymptotes, remember that's where we want to take the limit as x approaches infinity of our function. This is good practice for our final exam, which is coming up soon. And so when I do that, remember when x is approaching infinity, we just take the highest power of x in the numerator and denominator. So that gives us 2x over x, which simplifies to 2. So y equals 2 is our horizontal asymptote. Okay, so that gives us a decent amount of information about this function. Now we're going to ask about the stuff that we've been doing more recently. So where is this function increasing? Where is it decreasing? And where do we have local maxes and mins? So in order to do that, we need to find the derivative, and we'll use the quotient rule. So I have low times d high. D high is just 2 minus high. D low is just 1 over low squared. That's x plus 2 quantity squared. Okay, let's simplify this. So I'm going to have 2x plus 4 minus 2x minus 3 when I distribute everything over x plus 2 quantity squared. The 2 x's go away. I'm left with 1 over x plus 2 squared. Okay, there are no places that this is equal to 0, but the denominator is 0 at -2, so that's my only number for the number line. If I plug in a number smaller than -2, like -3, I'm going to have 1 over a positive number because it's something being squared. So I'm going to get something positive. And then when I plug in something bigger than 2, like 0, I also get a positive number. So this function is increasing essentially everywhere except for where it's undefined. So -infinity to -2 and -2 to infinity. It is never decreasing. And it has no local maxes or mins because there are no places where the derivative changes signs. That's kind of fun. Okay, so now we have to find the second derivative in order to determine concavity. So we're going to have to find the derivative of this guy. So let's multiply out that denominator to get x squared plus 4x plus 4. So my low d high, my d high is going to be 0. So I'm going to have low d high is just going to be 0. Minus my high, d low is 2x plus 4x all over x plus 2. I'm going to do x plus 2 squared and then squared again, x plus 2 to the 4th. Okay. This will be 0 oops, sorry, I put an extra x in here, didn't I? This will be 0 when the numerator is 0, which is at -2. And so -2 again is the only number I need on my number line. That's also where the denominator is 0. If I plug 0 into this expression, I'm going to get a negative number over a positive number. So I'm going to get a negative number out. If I plug in, oh, wait, sorry. That was what happened when I plug 0 in. 0 is bigger than -2. When I plug in something smaller than -2, like -3, I'm going to have a negative times a negative, which will give me a positive, and the denominator is positive. So I'm going to have a positive. So this function's concave up on -infinity to -2, concave down on -2 to infinity. And we do not have any inflection points here because the sign of f double prime changes at -2, but -2 is not in the domain of our original function, so it's not considered an inflection point. Okay, so let's see what we have here. So for values less than, well, let's actually look over here because we've got 2 points over here. So for values bigger than -2, my function is increasing and concave down, okay? And I need to connect those dots and deal with the asymptotes. So let's try and deal with the asymptotes. So if I deal with the asymptotes, if I connect the dots like this is increasing and it is concave down. So that looks like my graph here. Over here for values less than -2, we're still need increasing, but now this needs to be concave up. So to draw something that respects those asymptotes is concave up and increasing over here, I draw something like this. So this is my graph. It's a lot to put together. And so we'll just do a few examples in class and get some practice using all this information.